Hi, Aryaz. Are you there?
Hello. Yeah, yeah.
Yeah. So you can prepare and share your screen.
Um, can you
Okay.
see this? Um,
Yeah.
yeah, great.
Okay, I can see the full screen. So the first speaker is Aryaz Eghbali. He's from University and of Stuttgart. So let's start now, and you have about less than 20 minutes. And after the talk, we will have some minutes for questions and answers. Okay, so please start.
Thank you. Hello, everyone. Thanks for attending this session. I hope that you'll enjoy the results of our research and hope to see you in person in the future conferences. So I want to talk about our project that I've been doing at the Software Lab at University of Stuttgart on string-related bugs. So you have probably seen strings in many use cases in different parts of the program, from referring to files or websites to embedded code from a third language in a host language, or importing libraries or modules using their names, or also accessing properties of objects using the name of the field. And in today's software, the strings are used widely, and that's one of the reasons that we are interested in the bugs that occur in them. So one of the features of strings is that they're essentially a sequence of characters, and that means that they can hold almost any value. That makes them a very powerful type, but also because they can hold almost any sequence of characters, it means that there are very limited checks on them. And this makes them prone to bugs. And this is another reason that studying the bugs in strings is very important. And also, they hold values that might have meaning, which the tools usually ignore. So what are we interested? We want to see why string bugs happen, what are the root causes. We also want to know what happens when these bugs occur, what are their consequences. And also, we want to know how developers fix these bugs and whether it's possible for an automated tool to fix or repair these uh, bugs. We also looked into which components of the software are mostly affected by these bugs, and we also checked whether existing tools can detect any of these bugs. So what we studied were a set of 13 JavaScript projects. And the reason that we chose JavaScript is that it uses strings in many different ways, and it's also used in many different domains. What we did was we selected a series of popular JavaScript projects on GitHub based on their star ratings, but we also aimed for diversity both in terms of the size of the project and also the domain and their use cases. And as you can see, we came up with this list of projects, and some of them are used in thousands or millions of other projects, which makes the bugs occurring in these projects very important in the whole software industry. And the approach that we took for collecting the bugs was that we selected the commits of these projects from GitHub, and then we filtered out the code changes with more than 4 lines of code. And this leaves us with only small code changes. And then we inspected manually to find out the string-related bugs. And what resulted was a set of 204 string-related bugs that we have published as our data set. So what are these string-related bugs? The first criteria that we chose was they should be only applicable to strings. So these bugs cannot happen with other types. They can happen with string literals, other string types or wrappers, but not with any other types. So if a bug can happen, for example, both for integers and strings, we just ignored it. We didn't include it in our data set. We were also only interested in bugs, so we only looked for bug fixes, which means that in the code changes, there's a commit message. And if that explains, for example, this is a bug fix, or reference an issue number, or in some way explain that with this commit, some problem was fixed, then we chose that as a bug fix. So any refactorings or addition of new features were excluded from this work. We were also only interested in JavaScript, so we only looked into the JavaScript files, not documentation files or third-party libraries, even if they had JavaScript code inside them. So the first question was, why do these bugs happen? And what we came up with was this hierarchy of categories of bugs. This would be very useful for developers to look out for and avoid, but it would also be useful for tool builders to know what categories of bugs can happen with strings so that they can address it in their tool. And what we found was that the most prevalent category of bugs are string literals. Either the string literal is incorrect, like the first example, or the developer should not have used the string literal at all. So it should either have been a configuration file value, or it should have been derived from a function. The second most prevalent root cause were incorrect regular expressions. And this requires more explanation, but you can see a further categorization of regular expression bugs in our paper and also in the data set. But to mention a few, we have some grouping problems of regular expressions, or the anchors, the start anchor or the end anchors, some optional values, and so on. You can see a few of these examples below. Another one of the root causes were incorrect references to other languages or resources. So either the code embedded as a string was wrong. It could have been a syntax error, or it could have been some logical errors. Or references to other resources like files or databases or other websites were wrong. There were a few API usage problems. So for example, in the example that you can see down below, that replace API returns the new string. It doesn't replace the string in place. So this is one of the bugs. This category contains bugs related to string API. And then we had a lot of problems with comparison and operations. So either the comparison had some issues, or there were some missing checks or operations, as you can see in these two examples. One of the other problems were the string type itself. There were many cases that the value should have been cast to a string or was a different type and should have been a string type. Knowing these root causes helps the developers be aware of them and avoid them, as I mentioned before. But it also shows us that very few root causes cover most of the bugs. So the string literal problems, regular expression problems, and the comparison and operations make up most of the problems with strings. And a good target would be here to start building bug detection tools. For example, one that could happen is validating references or external resources, or also checking the embedded code inside the host language. So next, we look into what happens when these bugs occur. And as you can see, most of the bugs that we found caused some incorrect output. And this output can be a textual output or a graphical user interface output. Then we had a lot of tasks being left undone, either partially or completely. There were a few error messages. We also had some bugs occurring for specific operating systems or softwares. For example, a bug caused some problem on Windows or on Firefox. Then we had a few test failures and some corruptions in files. And as you can see, there are very few test failures here. So knowing these consequences would help developers implement better tests. As you can see here, many of the bugs are left untested. And we unfortunately didn't find any clear correlation with the root causes, whether a specific root cause causes specific consequences. We then looked into how developers fix these bugs and whether an automated repair tool can fix them. So I mentioned in the methodology slide that we filtered out the bug fixes with more than 4 lines of code change. But within this limit, you can see that most of the bugs are fixed within 2 lines of code change or fewer than 40 or 50 characters of change. This means that the bugs can be fixed with very little change. Then we looked for repair ingredients, the tokens that are required to fix these bugs. We looked for a window of 100 lines around the bug location to see what ratio of these repair ingredients are available inside the code so that an automated tool could look for them and fix the bug. And as you can see, more than half of the repair ingredients required are usually present within 100 lines. So knowing that these bugs are small, the fixes are small, and a majority of repair ingredients are available within 100 lines, this makes it a very good potential for an automated repair tool to fix these bugs automatically. We also looked into what components of the software are affected by string bugs. And as you can see, most of the bugs we found appear in the core components, but that's mostly because the core component is usually larger. We also found bugs in the utility functions, testing functions, user interface, building scripts, and a few in demo section. So this means that all the components in the softwares are prone to string bugs, and we didn't find any correlation with the root causes, whether a specific root cause affects one component more or less. We also wanted to know whether existing tools can detect any of these bugs. So we chose JS Hint, which is a very popular JavaScript linter. And we found out that it can only detect one of the 204 bugs that we found, which is an invalid regular expression, which is not really hard to find. So the existing tools cannot detect most of these bugs. So this makes building tools to detect these bugs very important. I want to mention that we have published our dataset. I encourage everyone to look into our dataset and work with it. There are also some directions for future work. For example, automating the manual process of finding these bugs, the bug fixes. Initially, I mentioned that we selected only small code changes, but automating that would make this study better. Also, strings hold values that have some meaning in them. And one could potentially look into that and see whether those meanings, for example, the value stored, for example, as a URL or a message to the user, that value can be used to infer or not. I want to thank all of you for your time, and I'm now open to questions.
Yes, thanks for this wonderful talk. So everyone, please raise your question in the session QA part, or also you can just open your camera and speak up. You can speak to the speaker directly. So any question? Okay, I will be the first. So first, thanks for the talk. It's wonderful to have various questions about the string-related bugs. So my first question is about the selection of string-related bugs. So I guess it's common to ask a question that how did you reduce the bias in the bug selection?
So thanks for the question. I mentioned in the first few slides that we filtered out the large code changes. So we ignored any code change with more than 4 lines of code change, and then we just manually went through the remaining ones to see whether they are string related or not. Does that answer your question?
Yeah, okay, thanks. I found a question in the session QA part. The question is, if we ignore the regular regression bugs, how much of the semantics of the string is necessary to find and fix bugs? That's about the regular expression bugs.
Sorry, does that mean the repair ingredients?
You can find the question in Huba. So the question is, if we ignore the regular expression bugs, how much of the semantics of the string is necessary to find and fix the bugs?
Okay, so I showed in this chart here that usually more than half of the tokens are there. But in this analysis, we used strings and regular expressions as only one token. Which means that we ignored the values inside them. But there might be the case that the whole string or the whole regular expression appears somewhere else in the code. But we didn't further analyze whether we can make up the string within itself or the regular expression. I hope that answers the question.
Okay, and thanks for the speaker and thanks for the question raised by Julia. Did that answer your question, Julia? I hope so. Okay, so is there any other question? Okay, so I will ask another small, quick question. So in many of your research questions, you have the takeaway messages. And I saw that you mentioned in some of the bugs, you didn't find a correlation between the bugs and the strings and the root causes. So my question is, did you find anything interesting about the root cause? I mean, so you have checked so many, over 200 bugs, maybe you can find something interesting.
Unfortunately, there isn't something which is not intuitive. As I mentioned, most of the bugs are caused by very few root causes, like mistakes in string literals, regular expressions, and checks operations on API usage, which is not surprising. But I'm not sure how to answer that. It's not like that we didn't know that these are very common problems with strings, but having them with numbers is assuring.
Okay, so let's recall the last question raised by Julia. She asked that, for example, do we need full natural language processing to fix the bugs? It's also related to the regular regression bugs. And another question, maybe also related, is are there any common patterns that one can fix this kind of bugs? Are there any common
the
patterns?
Regular expression?
No,
the regular
about
expression?
the string-related bugs.
Okay. So regarding the first question, that's a very interesting direction, and I encourage the researchers to look into that because the strings have some meanings in them. Using natural language processing would be a very nice idea for detecting bugs, but it depends on whether people use meaningful, for example, variable names or values inside the string. So I'm not sure about the results. For the second question regarding the patterns, the higher order categories and patterns are the ones that I mentioned. And we have a few examples in our paper as well. But there weren't any specific patterns that were more fine-grained that we could detect. We have some subcategories in our data set for other patterns that were not as common. You can check those out, but I don't have any more details on these patterns to share here.
Okay, thanks a lot, Aryaz. Thanks for your presentation, and let's move to the second
Thank you very
talk.
much.
Thanks. So hi everyone, this is now the ASE session R35. You are now looking at bugs and automated repair. So we are now in the live session of ASE 2020. So if you have any question, you can post your question in the session QA part in the Hova app. And now it's the second talk